If you remember, when we discussed about an example, z equal to 4x cube 4x cube y square minus 4x square plus y raised to 6 plus 1, we found that the partial derivative with respect to x as 12x square y square minus 8x, and the partial derivative with respect to y as 8x cube y minus 6y raised to 5. Right. See, when we found the partial derivatives with respect to x and y, we again got functions of two variables. Right. Again here zx is a dependent variable, or this value as a dependent quantity, and we have independent x and y here. Right. If it is the case, can we think about differentiating these zx and zy further with respect to x and y, or the partial derivatives of zx and zy as we have done for z? That is possible, and they are called the higher order or the second order partial derivatives, the partial derivatives of the partial derivatives. Okay, so let's see the possibilities. We move out of the example now. Let's generalize things a little more. Suppose we have a function z equal to f of xy. Okay, we find the partial derivatives zx and zy. Right. Zx is a function of x and y, and zy is a function of x and y. Then zx can be again differentiated with respect to x and y. Right. So following the same notation, zx can be again differentiated with respect to x, zx x, and zx can be again differentiated with respect to y, zx y. Similarly, zy can be differentiated with respect to x, and zy can be differentiated with respect to zy, and the partial derivative of zx with respect to x is sometimes denoted as zxx, and the partial derivative with respect to y of zx is zxy, and the partial derivative with respect to x of zy is zyx, and the partial derivative of zy with respect to y itself is called zyy. Okay, so this is how we usually denote these things. And we have another notations like dou square f by dou x square, and here we have dou square f by dou y dou x. See, when we turn into this notation, remember that the order changes. This means f is first differentiated with respect to x and then with y. Okay, so the expression, the order of expression reverses in these two notations, remember that. And here we have dou square f by dou x dou y, and dou square f by dou y square. Okay, we may end up at a position where what are the differences between dou square f by dou x dou y. So let me just clear this off. You may possibly think that our dou square f by dou x dou y and dou square f by dou y dou x are the same. See, the order changes here, or does it make any sense? See, in general case, they are not equal. Generally, they need not be equal, but there are cases where there happens to be equal, like the situation where we have continuous second order partial derivatives and all. We will discuss that soon in the course. So for now, remember that dou square f by dou x dou y and dou square f by dou y dou x need not be always equal. Okay, so the order matters. Alright, so they are the higher order partial derivatives, and these derivatives like dou square f by dou x dou y and dou square f by dou y dou x, are sometimes called mixed partial derivatives. Mixed partial derivatives. Mixed partial derivatives. Right. By the sense that x and y comes mixed. We first differentiate with respect to x and then with respect to y, or we first differentiate with respect to y and then with respect to x. So in that sense, these may sometimes be called as mixed partial derivatives. Okay. See, this can be done again and again. Need not be ended at dou square. So this can be extended to dou cube f by dou x x, like dou x x x or dou x cube, or dou x dou y dou x, or dou x dou x dou y, so on. This can be repeated several times until the derivative remain defined. See, we have seen that derivatives are not always defined. So this can be repeated several times as long as the derivative remain defined. Okay, so we have seen that these two need not be equal. These two need not be equal. But remember that if the function has continuous second order partial derivatives, then fyx and fxy will be equal. Or dou square f by dou y dou x and dou square f by dou x dou y will be equal. Okay. So that's about the higher order and mixed partial derivatives. I hope we need not to go to any examples for this case, since it can be easily deduced from the previous case of differentiation with respect to a variable. Now, all these ideas and concepts which we have explained for two variables can be easily extended for functions of three variables. In fact, functions of any finite number of variables. Functions of three variables, say for now. So consider a function w equal to f of x, y, z. W equal to f of x, y, z. Then we can define partial derivative of w with respect to x, partial derivative of w with respect to y, and the partial derivative of w with respect to x, since w depends on x, y, and z. So if there is a change in x or a change in y or a change in z, that can seriously change w. And if there is a change, we can think about the rate of change. So partial derivatives exist. Or we can think about partial derivatives. We don't know whether they exist or not. Okay. So, how do we define wx? Using the limits. This will be a limit delta x tends to 0, f of x plus delta x, y and z will be remaining the same, minus f of x, y, z by delta x. Similarly, with respect to y, we will have a small increment of delta y with the y part, and for wz, we will have a small increment of delta z at the z part. Right. So everything we have seen for two variable cases can easily be extended to the three variable case here. All right. If you want, we can go for an example here. Consider the function f of x by z equal to, z or t, whatever. Let's choose to be t. See, these are just variables, need not be x, y, z, and z always, can be p, q, r, s, or anything. So let f of x, y, z equal to e raised to minus 3 by d cos x sin 6y. So cos 4x sin 6y. Okay, so can we make an attempt to find the first or the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to t? See, all these are functions of x, y, and t again. maybe we expect them to be functions of x, y and t. Okay. So can we try to find out? How do we find the partial derivative with respect to x? We will simply differentiate the function with respect to x, keeping all other variables here y and t as constants. So let's try to differentiate. So here, if we differentiate with respect to x, we will keep y and t as constant. So e raised to minus 3 pi t is a constant, and sine 6y is again a constant. So let's take them out. And what's left here? Cos 4x. So what is the derivative of cos 4x with respect to x? Is minus 4 sin x, right? Minus 4 sin x. So the fx will be, let's take the constants out first. E raised to minus 3 pi t into sin 6y into 4 minus 4 times sin 4x. So if you rearrange this for the sake of comfortness to read, minus 4 e raised to minus 3 pi t sin 6y sin 4x. Right. So this is the partial derivative of f with respect to x. Now let's see what is the partial derivative of f with respect to y. See again, this could be a function of x, y and t. So if we differentiate with respect to y, let's keep t and x as constants. So let's take the constants out first. E raised to minus 3 pi t is a constant into cos 4x is a constant. And the derivative of sin 6y with respect to y is 6 into cos y. So the derivative is e raised to, see, we have a 6 here. 6 e raised to minus 3 pi t cos 4x cos y. Right. So this is the partial derivative of f with respect to y. Similarly, with respect to t can be calculated out. Ft of xy t is, see, if we differentiate with respect to t, everything else in all other variables has to be treated as constant. So cos 4x is a constant, sin 6y is a constant. So let's take them out first. Cos 4x into sin 6y into the derivative of e raised to minus 3 by t. See, this is of the form e raised to minus ax, which has the derivative minus a into e raised to minus ax. So this is into minus 3 pi into e raised to minus 3 pi t. Right, so the derivative on rearrangement will be minus 3 pi e raised to minus 3 pi t cos 4x sin 6y. Right. So this is the partial derivative of f with respect to t. Okay. So in the same way, see, you can again differentiate this with respect to x to obtain ftx. Again with respect to y to obtain ftxy. So you can differentiate this any number of times until the derivative remain existent, or until the derivative exists. Okay. So you can simply use everything we defined and explained for 2 variables, for 3 or 4 or any finite number of variables. The next is about the chain rule for partial derivatives. See, hope you remember the chain rule for ordinary derivatives, which we have already seen in the previous classes maybe. Like if you have a function of single variable, say like y equal to f of u, where u is again a function of x. Suppose y equal to f of u is again a function of x. This gives us an intuitive idea that y can be expressed as a function of x, or y can be thought of as a function of x. In that case, if y can be thought of as a function of x, we can think about dy by dx. Right. See, y depends on u and u depends on x. So obviously y depends on x. So a small change in x may change u, and a change in u can change y. So a small change in x can change y. So there could be a rate of change of y with respect to x. Right. So we had the chain rule to find the derivative of y with respect to x as dy by du. This can be easily found since y is directly a function of u into du by dx. This can also be easily found since u is directly a function of x. Okay, so dy by dx was actually found as dy by du into du by dx. Never ever think that this is not obtained by simply cancelling out du and du. This du is not a number, not a term, and not even a variable. It is an operation or an operator which cannot be cancelled out at any cost. Right. So this comes from the chain rule. Okay. Similarly, we have a chain rule for partial derivatives. Suppose let's examine the two variable case first. Suppose we have a function of two variables, say z equal to f of xy. Okay, and x is a function of, or let's use u and v here. Things will be a little more clear if you use u and v. So suppose we have a function z equal to f of u v, and u is again a function of x and y. Say u is g of xy, and v is a function of again x and y. So what do we have here? Z is a function of u and v, and u is a function of x and y, and v is a function of again x and y. So z can be intuitively thought of as a function of x and y, since z depends on u and v depends on x and y. So z depends on x and y. Right. Similarly, the small change in x can change u and v, and that change can reflect in z, and a small change in y can change u and v, and that change may reflect in z. So there is a possibility that we can think about dou z by dou x and dou z by dou y. Right. Dou z by dou x and dou z by dou y can easily be found with the formula dou f by dou u into dou u by dou x plus dou f by dou v into dou v by dou x. Similarly, dou z by dou y can be found as dou f by dou u into dou u by dou y plus dou f by dou v into dou v by dou y. Right. So this expression gives you the partial derivative with respect to x when we have z as a function of u and v, and u and v as functions of x and y, and this gives us the partial derivative with respect to y if with the same case. Right. So I'll just give you a practical example which you can solve yourself. A simple one. Suppose z equal to say u square minus v cube. Let u equal to e raised to 2x minus 3y, and v is equal to sine of x square minus 2y square. Okay, find dou z by dou x and dou z by dou y. Alright, so how do we find? Dou z by dou x can be found as dou z by dou u into dou u by dou x plus dou z by dou v into dou v by dou y. So again dou x. We are differentiating with respect to x here. Okay, if it is the case, we need to find dou z by dou u by dou x, and these are simple. We can directly substitute them. What is dou z by dou u? Z equal to u square minus v cube. So if you differentiate this with respect to u, keeping v as a constant, you will get 2u. minus v cube will have a derivative 0 since it is independent of u into dou u by dou x. See, u is equal to e raised to 2x minus 3y. So it will have the derivative with respect to x. See, the coefficient of x is 2 here. So 2 times e raised to 2x minus 3y plus what is dou z by dou v? Z equal to u square minus v square. U is independent of v. So minus v cube will have the derivative minus 3v square into what is dou v by dou x. V is equal to sine of x square minus 2y. So again we will have to use the chain rule for single variable cases there. So it will be 2x into cos of x square minus 2y square. Right. So this is to be all. So if you want, you can simplify this down to obtain a nice and beautiful expression, but doesn't matter, right? So similarly, you can find dou z by dou y as well. We are not going to that for now. It's pretty easier as this. Okay. And this chain rule can also be generalized to any number of variables. Any number of variables. Suppose we have a situation where we have a function z equal to f of say u1, u2, etc. up to un. We have n variables in the function f, and suppose each this un or ua's are functions of say x1, x2, etc. up to say xk. So the setup here is we have a function f of n variables, and each of these n variables ui's are functions of k variables. Right. If it is the situation, the partial derivative of z with respect to an x, say xi, can be found as dou z by dou u1 into dou u1 by dou xi plus dou z by dou u2 into dou u2 by dou xi plus etc. plus dou un by dou z by dou un into dou un by dou xi. Right. So this is a still mere generalization of the chain rule which we have seen and used before. Okay. So this is how we make use of chain rule in partial differentiation.